Hi, let's talk about filters for a bit. By the end of this video, you'll know how much extra integration time a 12nm narrowband filter really costs you, and whether the upgrade to a 5nm bandwidth is worth hundreds of dollars. So I have two filters in my hand. Filters in astrophotography are used to block light pollution and only let certain wavelengths through. Higher quality filters let less light pollution through, but they're more expensive. But is there really a difference between a filter that blocks 90% of light pollution versus a filter that blocks 95% of light pollution? How much better in actual measurements are higher quality filters? I don't know, but let's do some tests. I have 12nm HA and O3 filters and 5nm HA and O3 filters. Is it worth it to spend the extra money? To do the tests... Hi. I thought for a second it was going to be Dr. Detail has a message for you. Dear 3D counterpart, I am currently on an expedition to the intergalactic subdivision of the Null Protectorate. I know you want to test filters using your telescope in real-life conditions. Do that. But there are people out there who think that traditional signal processing theory doesn't apply to astrophotography. Our job isn't to prove people wrong or right. We are here to test hypotheses and try to find out what idea is closer to the truth. Figuring out what is right is more important than figuring out who is right. That's actually pretty profound. There's a life lesson in that, I'm sure. I know you're trying to figure out some life lesson in my words. This isn't a philosophy channel. Do computer simulations before analyzing data. If the data and the predictions do not match, then the doubters may have a point. If the predictions match, then we can be more confident in our results. It's a win-win. With a feeling of naturally occurring dopamine, Dr. Detail. But this is going to take so much more work. P.S. I know you think this will be a lot of work, but the viewers will appreciate it, and many of them who aren't subscribed will subscribe and like the video. Some may even become Buy Me a Coffee or channel members because they appreciate the effort. Well, okay, it may be a lot of work, but I am confident we'll learn something. Welcome to Deep Sky Detail. So the big question for you is, do you really need better filters in astrophotography? Can you get away with cheaper 12nm bandpass filters if you're going to do narrowband imaging? And do filters affect every part of the image the same? For gathering data, this is my setup that I'm going to be using. It's my Orion ED doublet with a 0.8x reducer for an effective ratio of f6. All images were taken with my Orion Sirius mount. I'm using my ZWO 294mm Pro camera. So filters aren't perfect, and one way to help determine how imperfect they are is through their bandwidth, measured in full width half maximum or FWHM. The larger the FWHM, the more non-target photons get let in. I'm testing my Optilong 12nm bandwidth filters in this filter wheel for both HA and O3. And then I'm going to be comparing them to my SV Boni's 5nm O3 and HA filters. I'm going to do my tests on 4 targets. While I'm imaging these targets over the next few weeks, I'll be working on the simulations Dr. Detail asked me to do. For the simulations that I'll use for my predictions, I'm going to use the bandwidths I measured using my DIY spectrograph. For the Optilong filters, the bandwidth was measured at 12.7 nanometers, and the SV Boni filters were measured at 5.9. They're very close to what is specified. But before I analyze any data, I wanted to get some predictions for how the filters could behave based on SNR theory. For all the analyses and simulations, I'm assuming no bandpass shift. If you're imaging at f4 or f3.5 and lower, then you might have the wrong filters if they don't account for bandpass shift. And do filters affect every part of the image the same? So as I mentioned in my previous videos, I've been working with another astrophotographer, Brent, to help model the effectiveness of filters. A lot of the simulations were influenced by our conversations, and Brent gave me a lot of good ideas. What I'm about to show you is an imperfect simulation, but I think the fundamentals are sound. Brent has a lot of cooler ideas, and I'm sure he's going to have a video about that soon. Now, I did these simulations before I did any real-world SNR measurements. I figured that it is a good way to make sure that the experiments match the theory, and to get sound predictions. If the experiments do match the theory, that would be good. But if they don't, then there's probably something weird going on and some expected noise that I'm not accounting for. But for now, let's go over the simulation. So here is a visualization of what the O3 simulations are doing. On the x-axis is the wavelength of light pollution that travels through your objective lens. On the y-axis is the proportion of light that gets through based on the bandpass curve of the filter. Based on my light pollution, I estimate that around 2,300 photons hit each pixel on average during a 60-second subframe using my luminance filter alone. I estimated the light pollution profile of my area by creating a custom light pollution histogram and sampling from that histogram. I then randomly sampled from that distribution around 3,000 times to get photons of various wavelengths. I oversampled because I'm taking into account my camera's quantum efficiency. More on that in a bit. Then I simulated whether a photon represented here as a yellow moving line would pass through the filter. Once it hits the transmission curve, it either passes through or is blocked. The chance of it being blocked is like a coin flip, but the coin is biased based on the transmission curve. If the light pollution is at 500 nanometers and the filter is an O3 filter with a peak transmission of 0.9, then the light pollution has a 90% chance of going through, roughly. On this graph, light pollution successfully getting through is represented by a yellow expanding dot. Light pollution that gets rejected is a red X with a circle around it. I also looked at my camera's quantum efficiency, but first I've got some preliminary results. Okay, so I've been imaging 4 targets: NGC 7822, Messier 16, IC 1805, and IC 5070 for a few weeks. So let me show you what some of the calibrated subframes look like. I've been taking 150-second subframes. Usually I take 300-second subframes for narrowband, but I wanted to eliminate third variables as much as possible, like seeing and transparency on the subs. And I would take a 150-second sub with one filter, switch filters, and take another sub. That way, not too much time has elapsed between filters of different bandwidths. So let's look at these subframes side by side. So I've got the Pelican Nebula here open in GIMP, and this is what we'll look at. This is the 5 nanometer filter, and this is the 12 nanometer filter. They've both only had an auto stretch applied with no other further processing. The 12 nanometer filter seems like it has a bit less contrast. And if we zoom in here, the areas of the dark nebulae here are less defined. Let's turn on the 5 nanometer filter real quick. And you can see there's a little bit more definition in the dark nebulae, a little bit less noise. So this is the 12 and this is the 5. I'm not sure how much of this is coming through with YouTube's compression, but I can see differences between the subframes. If we zoom out, this is the 5 nanometer filter. It looks pretty clean, pretty nice. Let me turn that off. And this is the 12 nanometer filter. See a little bit more noise in this 12 nanometer filter sub. So don't get me wrong, the 12 nanometer filter is by no means bad, but let's again try blinking them back and forth just to see things again. So here's the 12 and here's the 5. 12, 5. The 5 nanometer filter just seems a bit more, I don't know what to call it, punchier, contrastier. Either way, visually, the 5 nanometer subframe wins in my opinion. But these are only 2 data points. You can get a perfect correlation with just 2 data points, which is why anecdotal evidence can be so tricky. Sometimes it really turns out to be true, but it might not. So we need to combine the data to get a better estimate of the SNR to be confident. But before that, we need to finish our simulations because we do want to know, do our results actually support astrophotography theory? So I need to simulate my camera's quantum efficiency, meaning I counted how many photons would be detected after they passed through the filter based on my camera's QE. This final count is the expected light pollution noise for the 5 nanometer filter. All of this is a lot of work, but it's not enough. There are simulations. We can do it again. In fact, I then repeated the whole simulation 2,000 more times. This gave me a baseline light pollution for that filter. You know, this whole video was quite a bit of work, both simulations and testing in the sky. I couldn't do it without my Buy Me a Coffee members and YouTube channel members who funded the purchase of the 5 nanometer filters. If you find this useful, consider becoming a member too. If you can't do that, then subscribing and liking also helps. While I was doing the simulations of the 5 nanometer bandwidth, I also simulated the 12 nanometer bandwidth at the same time. I then took the ratio of the light pollution values to get a distribution. I then repeated the whole process for my HA filters. So we have the light pollution noise. That's good. But we also have to add in the read noise, the dark current, and the deep sky object noise to get the total noise for the SNR measurements. I used values from my camera and my settings for the read noise and dark current noise. I'll get to the DSO noise in a second, but kind of keep in mind that these simulations are only for one pixel on one subframe, and it gives us the total noise of that pixel. But how do we estimate the SNR? That's not too complicated, but let's come back to that. So in between cloudy nights, I've been gathering data. So let me break it down. For each hydrogen alpha filter on Messier 16 or the Eagle Nebula, I got 1,500 seconds worth of data. So 1,500 seconds with the 5 nanometer filter and 1,500 seconds with the 12 nanometer filter. So this is a hard target for me because the trees block my southern sky. And so I didn't have a lot of time imaging it. For the Pelican Nebula, I got 2,250 seconds for each of my HA filters. For NGC 7822 or the question mark nebula, I got 5,250 seconds of data. And then for the Heart Nebula, I got 4,200 seconds with each filter. So all in all, that's about 7.3 hours. I think we should be careful though, because hours by themselves are not data. It's really the photons. 10 minutes of data for the Eagle Nebula might give us 10 times the amount of photons that the question mark nebula does. It's the photons we're counting to determine the signal. The more photons we gather, the more data we have. I kind of want you to keep that in mind because now I'm going to give you the O3 numbers. For O3, for M16, the Eagle Nebula, I got 1,500 seconds each for each bandwidth. For the Pelican Nebula, I got 0. Clouds suck. For NGC 7822, I got 3,450 seconds with each bandwidth. And then for the Heart Nebula, I got 3,150. All in all, I was only able to capture 4.5 hours for O3. So not only do we have less integration time, O3 is a weaker signal, meaning even if integration time were the same, we are counting fewer photons. So my question is, even with this limited data, will it match our predictions? And what if the predictions don't match? I might have to remake every single video on this channel. I think we can peek at some of the stacked images in hydrogen alpha at least. So let's look at NGC 7822 or the question mark nebula. The real-world SNR analyses are going to take a sample of 151 parts of each image, and then it figures out each sample's brightness. It then finds the standard deviations of each of the pixels within each sample as the image stacks in order to estimate the SNR for that sample. So let's say we've stacked 2 subframes. It finds the average brightness of those pixels. That's the signal. To find the noise, it will take a pixel, figure out what its brightness is for sub 1, then compares it to the brightness in the 2 subs stacked to get a standard deviation. That's the noise. It keeps repeating this process until I've stacked every image. Now, the algorithm does do some corrections based on the surrounding pixels in the stack, but I found the process is actually pretty reliable. We'll talk about the actual results once I've done the analyses though. For now, let's take a look at these stacked images and just compare. So let's take a look at the 5 nanometer filter first. Zoomed out, the brighter areas look pretty smooth. The darker areas have a little bit of noise. So if we zoom in, we can see that there's noise in these darker areas, but there is definition here in the dark nebulae. For the 12 nanometer stack, I can definitely see more noise in the area. So this is now I've blinked to the 12 nanometer stack, and even zoomed in like this, I think we can see a difference between the noise profiles between the two stacks. So let's blink again between the two images. If we zoom out, we can see this is the 5 nanometer filter. The background looks a lot smoother. If we blink to the 12 nanometer filter, we can see a lot more noise in these areas. It's not quite as punchy as the 5 nanometer stack. Also, the stars in the 12 nanometer stack are also a little bit brighter. So if we, again, blink back and forth, you can see that for the 5 nanometer stack, the stars are a little bit more controlled. And the 12 nanometer stack, they are a little bit more bright. The question is, how much, if we zoom in, how much longer do I have to image with the 12 nanometer filter to get the results of the 5 nanometer filter? Well, let's find out. So for the simulations, how should we think about signal? Well, this might not be the best way, but I think it's a useful way. Let's just pretend we know what the signal values are. For example, say that we only have 1 photon's worth of signal coming from our deep sky object onto the pixel. Well, the signal in the simulation is 1, and the 1 would be added underneath the square root of the noise portion of the simulation. We then just divide 1 by the square root of all of the noise. So let's do a quick example of one iteration for our 5 nanometer hydrogen alpha filter with 1 hydrogen alpha photon hitting the sensor. If we have 1 photon's worth of signal, then we can add the signal's noise to the noise. Find the SNR. For the 5 nanometer filter, the SNR is 0.072. For the 12 nanometer filter, it's 0.0495. So the 5 nanometer filter has an average SNR that it's 1.5 times better. In this example, it's a little bit less, but there's going to be some random variation in each simulation. So on average, it's like 1 subframe with a 5 nanometer filter is worth 2.25 subframes for the 12 nanometer filter. That's like going from an f7.5 scope to an f5. So there is one huge caveat here. Huge. And that's filters only affect noise. They don't affect signal. The signal from the DSO is the signal. Filters don't really change that unless there are differences in peak transmission or something else weird going on, which there might be. So unlike increasing your aperture that increases SNR for all parts of the nebula, filters are going to affect brighter areas differently than darker areas. So we have to ask ourselves, how much better is SNR for part of the nebula that emits 50 photons on average per pixel per subframe? Well, if we do the calculations again, but assuming 50 photons worth of signal, then our 5 nanometer HA SNR is now 3.3, which is pretty good, and our 12 nanometer HA SNR is now 2.38. The 5 nanometer filter is only 1.38 times better now for this simulation. It's not as big of a difference. And this trend kind of continues. The more signal that comes from the deep sky object, the closer the filters are in performance. The red horizontal line on this graph is a theoretical point where both filters will perform equally in terms of SNR. It's at 1, meaning the 5 nanometer filter is 1 times better than the 12 nanometer. Or in other words, they perform equally. This score will never reach 1. The 5 nanometer filter will always outperform the 12 nanometer filter. As the signal coming from the DSO approaches infinity, the more this ratio converges to 1. So do the simulations match the data? For HA, I ran the statistics. On average, each sample gets about 100 to 150 photons per frame. Our predictions say that the 5 nanometer filter should get about 1.3 times more SNR than the 12 nanometer filter. And the results say it did. It got almost exactly 1.3 times more SNR. But what about for O3? Well, for the 12 nanometer and 5 nanometer filters, There was no difference in SNR. Really, it's the same. Does that mean signal processing theory is wrong? No. In fact, for our noise measurement, the 5nm filter had almost exactly half the noise as the 12nm filter. That's in line with the predictions. Something else is going on. The 12nm filter is so bad that it might actually be good. Well, from a certain perspective. For that explanation, you'll have to wait until part 2 of this series. But I'm fairly confident that the O3 results actually reinforce signal processing theory. If you have an idea about what is really going on, leave it in the comments, and I'll tell you if I agree. What does all of this mean practically? Well, narrower bandwidths improve fainter SNR more than stronger SNR. For most objects you image, you're not going to be getting a lot of signal per pixel each subframe. If I had to guess, even hydrogen targets are going to give you fewer than 500 photons, even in long exposures for the brightest areas of your image. For the dimmer parts, you may be looking at only 20 to 30 photons or less. There are, of course, exceptions like Orion, but I would say a 5 to 6nm bandwidth filter is on average going to be about 1.2 to 1.5 times better for SNR than a 12nm filter. That difference is actually pretty big. You're looking at needing 1.4 to 2.25 times less integration time with a 6nm filter than a 12nm filter on most targets to get an equivalent SNR. Just remember that accumulating SNR is not linear. Doubling your integration time does not double your image quality or double your SNR. So is it worth it to buy more expensive filters? If you are on a tight budget, then it might not be. But if you are limited and have limited imaging time, then good filters may be worth it. If you like this video, I'm sure you'll like a series of videos I did exploring how long each subframe should be. I've tested broadband with very short exposures, broadband with very long exposures, and narrowband. The results are pretty interesting. The playlist is here, and if you'd like to watch something else that the algorithm recommends, well, that video is here. Thanks for watching.